Welcome to the LemnaTec Academy. In this video, I will give you a deeper insight into the Lemna label tool. You may start the label tool from the desktop icon or from Lemna Experiment. If you started from Lemna Experiment, it will automatically open the right image to be labeled, open the previous labels for the same image created for the same machine learning model, automatically select the matching label class definition file if you made any changes there, automatically loads the predictions of the latest machine learning model created with this and other label files. And it selects the right output destination for the label file. If you started from the desktop icon, you will have to care about all this by yourself. On start, it will immediately request you to select the image to be labeled. But now let's get into it. I assume we are on a germination project. I will start the label tool from Lemna Experiment. If you start the label tool for the first time, you see this tutorial. Unless you check this checkbox, it will appear every time you start it. In addition, you can open the manual from the menu at the top right corner. In this menu, we have a couple of more entries. New image to label. This loads a new image to be labeled. You should avoid this if you start this tool from Lemna Experiment. Load labels loads a file containing previously created labels and makes this file the new default output file for the save operations. Import labels load labels from a previously created label file, but this time the name of the output file is unchanged. Save labels saves the current labels to the currently selected output file. Saves label as saves the current labels to another file and makes this the new default output file. Load ML results load predictions created by an ML prediction. Usually this prediction is created, among others, using this file. Help shows the aforementioned manual. And exit closes the program and saves all yet unsaved changes. On the right side below the menu, you find the toolbox. I will explain it in a moment. On the left, you find the images with its labels. Its name is found at the top. You see there's the current zoom factor and if there are unsaved changes as well. Below you find the name of the current label file. If you press Save Labels in the menu or use the respective shortcut, the labels will save to this file. You can zoom in and out this image using the mouse wheel with the pressed Ctrl key. Or you use the shortcuts Ctrl-0 to Ctrl-9. Ctrl-0 is zoom to fit the screen, Ctrl-1 is 100%, Ctrl-2 is 200%, and the rest are even higher zoom factors. I personally found high zoom factors like 500 to 900 very useful with this tool. The toolbox on the right has 3 sections. On the top we have the list of label classes. Since this tool was originally developed for germination analysis, the default names of these classes reflect this. But you can change the label names and colors using the Edit Labels dialog. In this dialog, you see the different label classes currently defined. If you double-click a name, you can change this name. Or change its color. One of these label classes is the background class. You can select it using these radio buttons. You can also define the default blocking width for each class. I will explain what this blocking width means later in this video. With the arrows on the right, you can change the order of the label classes. With the plus button, we can add another class if required. If you change anything here, this will be stored in a label definitions file. If you start the label tool from LemnaExperiment, its location is managed by LemnaExperiment. Otherwise, it will be saved in the same folder as the label image. In this label class list, you select the label class you will use next for your labeling. You can select them using the mouse or the shortcuts 1, 2 through 8. In the next toolbox, we have the actual label tools. We have currently 9 of them. Draw, free shape, line, bucket fill, morphology, relabel, pick label, auto shape, and diluted shape. I will explain them in detail in a minute. Some of them may have a parameter where you can change, for instance, the line width. Below this there are 3 radio buttons: Add, Remove, and Export. I will explain them as well in a second. Finally, we have the display options. I loaded a different image for which I have labels and machine learning predictions. With Show Labels, we can show and hide the labels we have drawn. I recommend to use a shortcut here. The shortcut key is the Escape key. The Show Machine Learning Results box is a tri-stack box. Unchecked, no predictions are displayed. Half-checked, the predictions are displayed in a very transparent fashion, but with their outline highlighted. Fully checked, the predictions are displayed only with low transparency. This way you may see a glimpse of the original image and the labels. The shortcut for Show ML results is the K key. Show ML errors highlights the difference between labels and predictions. With the transparency slider, you can change the transparency of the labels. The gamma slider is yet a better feature at the time of the recording of this video. It might not be present in your version of the label tool. With the gamma slider, you could change the gamma used to display the image. If you use a value below 1, this can make edges of objects clearer to view for the human eye. This does not change the image data used by the algorithm. In some cases, we have multiple exposures of the same image. In this case, you can add them using the plus sign here. If you do so, you can switch between them. Since they are only different exposures, these show the same content, but some structures might be easier to differentiate on brighter images and others on dimmer ones. This feature is not yet supported by LemnaExperiment. But let's start doing actually something with this tool. Let's focus on some seed. Let's focus for the start on this seed. I select the drawing tool, shortcut D, and draw the outline of the seed. Now I draw the outline of the seed. As I move the mouse cursor with the left mouse button pressed, I add more yellow pixels. The pixel color represents the label class. Currently it's yellow for the seeds class. If I accidentally label something wrong, as I did here, I can switch to the remove mode. If I draw If I move the mouse now with the left mouse button pressed, these pixels get removed. However, switching back and forth between add and remove could be clumsy. Therefore, we have an expert mode. In this mode, pixels are added if you press the left mouse button and removed if I press the right mouse button. If I have drawn a closed shape, you can use bucket fill to fill it. However, there's a limit on how many pixels you can draw at once. Therefore, if the shape is not closed, then almost the whole image would have been filled. These are too many pixels to be filled. Therefore, nothing happened except for a warning message below here. If we close the hole and try again, the shape gets filled. You can combine these two tools at the same time. This is a free shape tool. You draw an outline, and this outline is automatically closed. All pixels inside are labeled. So we can use this to label the surroundings of our seed. You notice probably something peculiar. The background pixels not fully reach the seed pixels. This is the effect of the blocking width. Let's zoom in a bit further. We see that there's not always a clear cut between seed and background. Some pixels are in an intermediate state. In order to avoid making decisions, what if such a pixel is background or seed or any other class, we do not label them at all. However, it is important to label borders between classes. These pixels are the hardest for the machine learning model to predict because they are surrounded by a mixture of different types of objects. On the other hand, it is even more important to label consistently. But this is particularly hard for these transitional pixels. Therefore, you can use the blocking width to avoid labeling them. By default, the blocking width for the background class is 1, 0 for all other classes. Sometimes you need to overrule this blocking. If so, you can use the Disable Neighbor Blocking checkbox. This is a tri-state box. In this state, blocking is enabled. In this case state, blocking is disabled for all classes but background. In this case, blocking is disabled for all classes. Let me show you quickly the other drawing tools. Line. It connects two consecutive clicked pixels by a line. The first click creates just a single point. This can be of advantage if you like to label long elongated objects like roots in a germination assay. Pick label changes the selected label class to the label class of the pixel you've clicked onto. It automatically returns to the previous selected tool. Sometimes we label some pixels with the wrong class by accident. You can fix this by selecting the correct class and using the relabel tool. If you click on the area of wrongly labeled pixels, they are changed to the selected label class. auto shape. This labels all pixels which have similar colors to the pixels you've clicked on and are connected. The similarity is determined by some heuristics. You can control the threshold of the similarity by the sensitivity parameter. If you select a sensitivity of 1, many pixels are selected. If you select a sensitivity of 12, only a small area is labeled. Please note that only pixels up to 500 pixels away from the point you have clicked on are included. The last tool I like to mention here is diluted shape. This works the same way as free shape, but labels only a random subset of pixels. There's also an undo buffer, which you can access using the usual Ctrl-Z and Ctrl-Y shortcuts. The depth of the undo buffer depends on the available memory. Training a machine learning model is an iterative process. Therefore, we need to update and fix labels as we iterate the machine learning model. Using the predictions of the previous round can be very helpful. Therefore, I will switch to another dataset. For this image, we already have previous labels and predictions. We can use the latter to improve our labels. If we start from Lemna experiment, these are already available. Otherwise, you have to load them from the menu using the Load ML Results entry. If we have loaded them, we automatically switch to the intermediate state of the Show ML Results checkbox. The labels of the predictions are drawn as a very transparent overlay with the edges of each area highlighted. As we toggle the checkbox or press K, we switch to the state where all predictions are displayed in a less transparent way, but we can still see the labels themselves and a glimpse of the image that we label. We can now correct places where we see errors. I like to add now a few hints for the best practices if you label for the LemnaTec machine learning algorithms. Inconsistencies and even false labels are more detrimental to the training success than missing information. That said, sufficient information of the borders between classes is also important. In later rounds, you can focus on parts of the images which turn out to be critical or hard to predict. By adding only those pixels, but not many trivial ones, you shift the focus of the algorithms towards the critical ones. You should not correct everything at once. Give the algorithms a chance to self-correct in later rounds. Therefore, you should fix only some instances of each error pattern. In later rounds, it's sometimes sufficient to just draw some white lines on places with an error, as I did here, in particular on roots, shoots, stems, branches, or leaves. You need to provide sufficient example pixels for all classes. This includes the background class and similar classes. For technical reasons, the algorithm cannot classify pixels at the edges of the images. These pixels in the images were automatically considered as background. The algorithm in LemnaGrid considers the most abundant class to be the background class. Sometimes we have small areas of misclassifications scattered in a much larger area. This is in particular the case if we have two very similar classes, or parts of one class looks very similar to another class. One example is a soil in rhizotrons for root analysis. This often contains small pieces which look similar to the roots themselves. In this case, we can use another feature of the label tool. Let me demonstrate this with an example from another data set. We have here prediction of roots in rhizotrons. Some soil parts are also predicted to be roots. These soil pixels look not too dissimilar to root parts, in particular of small root fragments. Furthermore so if we consider the limited view window of the ML algorithm. We can now select this checkbox to restrict labeling only to those pixels that are predicted to be root. Now we select background as label class. If we now use reshape to label the background between and around the roots, only those pixels are labeled that have been mispredicted to be root. Now we want to cover a bit of the neighborhood of these pixels as well. We use the morphology tool to increase some of these spots by 2 pixels. For the final feature, I need to switch the example again. In this example, we have labeled already a bit more pixels. We could use the 2 checkboxes for labels and ML results to check where the predictions and the labels match and where not. Or we use the Show Machine Learning Errors checkbox. This highlights all pixels which are labeled, but have been predicted differently than they are labeled. That was my introduction to the LemnaTec label tool. I hope you will find it now easier to label images to create your machine learning models. See you in another video.